Demystifying scikit-learn Gaussian process kernels, a deep dive. Gaussian processes (GPs) are a powerful tool for modeling and predicting data where the underlying function is assumed to be smooth and continuous. In scikit-learn, the Gaussian process regressor and Gaussian process classifier classes rely on kernels to define prior over functions. These kernels essentially capture the assumed relationships between data points and their corresponding outputs. Let's explore the intricate world of scikit-learn's Gaussian process kernels in detail. 1. The fundamental concept: kernels. At its core, a kernel function measures the similarity or codependence between two input points. In the context of GPs, the kernel defines the covariance between the outputs at these input points. This covariance function dictates how smooth and correlated the function is expected to be. 2. Key values in a typical kernel definition YAML example. Let's deconstruct a hypothetical YAML representation of a kernel. YAML. Kernel. Base kernel type. Type RBF. Kernel parameters specific to the type. Length scale 1.0. Length scale bounds 1 EO5. 10.0. New 1.5. Constant value 1.0. Constant value bounds 1 EO5. 10.0. Kernel type. This defines the fundamental type of kernel used. It's often a choice between the following. RBF radial basis function, a popular choice. It measures similarity based on the Euclidean distance between input points. Mattern similar to RBF but with more control over smoothness parameter nu. Rational quadratic offers flexibility in the smoothness and correlation structure. Dot product suitable for linear relationships between input points. Constant represents a constant covariance for all input points. White kernel accounts for noise in the data, independent of input locations. Kernel length scale, a key parameter for RBF and Mattern kernels. It determines the length of the correlation, i.e., how quickly the covariance decreases with distance between points. A smaller length scale implies that points close in input space have a strong correlation. Kernel length scale bound specifies the allowed range for the length scale parameter during optimization. This helps to prevent overfitting. Kernel.nu used for the Mattern kernel. It controls the smoothness of the resulting function. Higher nu values indicate smoother functions. Kernel constant value used for the constant kernel. It dictates the constant level of covariance. Kernel constant value bounds similar to length scale bounds. This restricts the range of the constant value during optimization. 3. Common kernel combinations and examples. Sum of kernels to capture more complex relationships. We can add multiple kernels together. Python. From sklearn, Gaussian process, kernels import RBF. ConstantKernel. White kernel. Kernel 1.0 RBF length scale 1.0 ConstantKernel constant value 1.0 white kernel noise level 0.1. This combines the smoothness of the RBF with a constant offset and accounts for noise with the white kernel. Product of kernels. The product of kernels allows for building more structured relationships. Python. Kernel RBF length scale 1.0 ConstantKernel constant value 1.0. In this case, the resulting covariance is the product of the covariances of the individual kernels. 4. Understanding the impact of kernel choices. The choice of kernel significantly influences the resulting model. RBF kernel leads to smooth, bell-shaped functions, capturing local dependencies. Mattern kernel provides control over the smoothness. Lower nu values lead to rougher functions, suitable for data with sharp changes. Rational quadratic kernel offers flexibility by combining multiple RBF kernels with different length scale values. Good for capturing both smooth and oscillatory patterns. Dot product kernel suitable for data with linear relationships. Often used for classification problems. ConstantKernel useful for modeling a baseline or offset in the data. White kernel adds noise to the model. Important for fitting noisy data. 5. Key considerations for choosing kernels. Data properties: consider the smoothness, linearity, and noisiness of your data. Prior knowledge: if you have prior knowledge about the underlying function, choose a kernel that reflects this knowledge. Model complexity: choose a kernel that balances complexity with computational efficiency. Hyperparameter optimization: use hyperparameter optimization techniques to find the optimal parameters for your chosen kernel. 6. Exploring deeper. Kernel learning: learn about techniques like automatic relevance determination to automatically determine the relevant input features. Non-stationary kernels: explore kernels that capture non-stationary behavior in data. Custom kernels: learn how to define your own kernels to capture specific data characteristics. 7. Caveats and challenges. Overfitting kernel parameters can lead to overfitting if not carefully tuned. Computational complexity: kernel-based methods can be computationally expensive for large datasets. Choice of kernel: choosing the right kernel is crucial and often requires domain expertise. By understanding the nuances of scikit-learn's Gaussian process kernels, you can unlock the full potential of these powerful tools for regression, classification, and other predictive modeling tasks.